Good day, everyone. My name is Chris Anthony W. Monopolio. I am from Western Mindanao State University, Zamboanga City, Philippines. I am the presenter of paper number 15711392008, and I am honored to present our research as part of the 13th International Conference on Information and Communication Technology. Today, I'll be presenting our paper entitled Eagle Vision Identification of Ice Disease in Agal, also known as Kappaphycus alvarezii, using YOLOv5. This study was a collaborative effort by myself and my co-authors. I am Chris Anthony W. Monopolio, and together with me is Mr. Anjover D. Mosquisa, Mr. John Samuel T. Talaver, Mr. Mark S. Atienza, and our advisor, Engineer Kevin Mark A. Bejarano from the Electronics Engineering Department of Western Mindanao State University. Here's the outline of my presentation. We'll go through the introduction, the objective of our study, methodology, results and discussion, and finally, our conclusion. Let's start with the introduction. Seaweed farming is a critical livelihood in coastal regions like the Zamboanga Peninsula, the third largest seaweed producing region in the Philippines. Seaweed farming provides multiple benefits, including using food, cosmetics, and pharmaceuticals, reducing ocean acidification, and supporting marine restoration. However, the industry is threatened by diseases like ice disease, which severely affects seaweed growth and quality, especially Kappaphycus alvarezii, locally known as Agal. Our goal is to support seaweed farmers in identifying this disease during the post-harvest stage before the drying process begins, using a more efficient and automated approach powered by computer vision and machine learning to help improve the marketability of their harvest. According to the study of Vairapan et al., the carrageenan content of healthy Kappaphycus alvarezii was significantly higher at 65.5% compared to only 45.1 in ice disease infected samples. This notable reduction of carrageenan yield highlights the detrimental impact of the disease on the seaweeds. Firdaus et al. Stated that the seaweed's retail value is also heavily influenced by its carrageenan content. As a result, if a significant portion of the harvest is infected, the overall market value of the seaweed will decline. The Seaweed Industry Roadmap of Bureau of Fisheries and Aquatic Resources highlights issues such as inconsistent road-dried seaweed quality and an unstable market for RDS. Developing this prototype would help improve quality control, which in turn may enhance the marketability and stability of RDS products. For the objective of the study, the main objective is to create a model that distinguishes between healthy and infected seaweeds using the YOLOv5 algorithm. To achieve that, we, number one, analyze visual characteristics. Through our collaboration with BFAR Region 9, we were able to successfully validate and distinguish between healthy and ice disease infected seaweed samples. Number two, design and develop an image processing device using Raspberry Pi 5. Number three, create a comprehensive dataset of seaweed images. This dataset will be used to train and validate machine learning models such as YOLOv5. Number four, evaluate the model's accuracy and real-world performance. Next, methodology. This conceptual framework diagram outlines the workflow of a system developed to detect and classify ice disease in Agal. The framework is divided into three main stages: the input, the process, and the output, which together describes how the system functions from data collection to disease classification. For the input consists of Agal images captured by a camera, processed using a YOLOv5 object detection model, TensorFlow for machine learning, and the Raspberry Pi for on-site processing. For the process involves using TensorFlow to train and improve the model's ability to detect ice disease from an expanding dataset of agal-agal images. YOLOv5 then analyzes the images to distinguish between healthy and diseased samples using a non-destructive detection method. And for the output shows the result of the system where the trained model checks the condition of agal-agal and classifies it as healthy, diseased, or undefined. Next is the system process flow. This flowchart shows the step-by-step process of detecting ice disease in agal-agal using YOLOv5 based system. It starts with capturing an image of the harvested seaweed, followed by pre-processing to prepare the image. The data is then annotated and split into training, validation, and test sets. The YOLOv5 model is trained to extract values and used for either real-time or batch detection. The system checks for any foreign objects in the image. If found, the result is marked as undefined. If no foreign objects are detected, the system assigns a health status, either healthy or diseased, completing the process. And the process is complete. Next is the hardware setup block diagram. This system consists of a Raspberry Pi 5 connected to a Raspberry Pi camera module 3 and a Raspberry Pi touchscreen display powered by a 27 watts USB-C power supply. Raspberry Pi 5 acts as the main processing unit, running the software and handling data from the camera and user interface. Raspberry Pi Camera Module 3 captures real-time images or video. Raspberry Pi touchscreen display provides a graphical interface for users to interact with the system. And the 27 watts USB-C power supply delivers stable and sufficient power to run all components of the system. For the dataset composition, 80% of the dataset was used for training and validation, with the remaining 20% for testing. The training set, containing annotated images of healthy and diseased seaweed, was further split into 80% training and 20% validation for accurate model evaluation. In image preprocessing, all images were resized to 320 by 320 pixels to keep a good balance between accuracy and speed. Different image augmentation techniques were used to help the model learn better while keeping important features of each disease class. Although no special loss function like focal loss was used, class imbalance was handled by adding more samples to the less common classes, especially the healthy and diseased ones, through careful augmentation that kept their key visual details. This is the YOLOv5 architecture. The YOLOv5 model was used for its good balance of speed and accuracy in detecting objects. It has three main parts: the backbone, which finds key features like edges and shapes; the neck, which improves feature quality at different scales; and the head that finalizes object location and class. The model was trained using a Tesla T4 GPU with PyTorch and Python. Training used techniques like stochastic gradient descent with momentum and weight decay to avoid overfitting. Pre-trained YOLOv5M weights were used for faster and more accurate learning, freezing the first 10 layers to keep basic feature detection. The model was later converted to TF-Lite INT8 format, reducing its size to about 65 MB and allowing it to run on a Raspberry Pi in about 118 milliseconds per images, making it fast enough for real-time use. Next, results and discussion. For testing trials, we tested the model using 10 randomly selected samples, each tested 10 times. This repeated testing aimed to evaluate the model's consistency in predictions and ensure stable performance across multiple runs. So we have here the image of a healthy seaweed. It was correctly identified 9 out of 10 thus resulting to 90%. Next, 9 out of 10, 90%. 10 out of 10, 100%. 10 out of 10, 100%. 8 out of 10, 80%. 10 out of 10, 100%. 10 out of 10, 100%. 10 out of 10, 100%. 9 out of 10, 90%. And 10 out of 10, 100%. The results show consistent performance, with most trials achieving 100% accuracy and a few achieving 90% or 80% due to lighting issues or early stage symptoms. For the confusion matrix, this confusion matrix shows the performance of the ice disease detection model on the validation set. The model correctly identified 482 healthy samples, that's 97% of the total healthy samples, and 222 diseased samples, that's 92.9% of the total diseased sample. It made 15 false positive by misclassifying diseased samples as healthy and 17 false negatives by predicting healthy samples as diseased. Overall, the model shows high accuracy and reliability in detecting ice disease in agal-agal, with only a small number of misclassifications. Out of the confusion matrix, we were able to solve for the performance metric results. Our YOLOv5 model achieved accuracy of 95.65%, precision of 97.09%, recall of 96.61%, and F1 score of 96.95%. These metrics show that the system is reliable in identifying ISIS disease with minimal false positives or false negatives. And lastly, for the conclusion, this study aimed to develop a YOLOv5 based machine learning system for real-time detection of ice disease in agal-agal seaweed. The system successfully identified healthy and diseased seaweed with 95.65% accuracy, demonstrating strong potential for automated disease detection in seaweed farming. Supported by local farmers and agricultural agencies, the system offers a scalable, objective, and less labor-intensive solution that enhances quality assessment, reduces economic losses, and supports sustainable production. Future work should focus on expanding the dataset with diverse conditions, upgrading hardware for faster detection, integrating remote sensing and IoT for continuous monitoring, using high-resolution cameras for improved accuracy, and enhancing YOLOv5 to detect multiple seaweed diseases for greater versatility. And with that, this brings us to the end of my presentation. We hope that the insights and information we've shared today can contribute meaningfully to the ongoing efforts in sustainable seaweed farming and inspire further innovation in this field. Thank you for your time and attention.